Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we're going to talk about 6.4, and I'll be very clear here. If you remember transformations from any of our past units, the transformations here are not going to be anything crazy. In fact, if you feel so confident with transformations from past units, this is going to just be extra practice with it. But we are going to talk about transformations of exponential and logarithmic functions. So, first off, let's talk about exponential functions. Exponential functions are always going to look like this. Y equals b to the x power. That is the parent function of an exponential. And we know from, past sections, exponentials are going to be a curve that sort of looks like this. It's going to start off near 0, and it's going to slowly start going its way up, like so. The thing about exponentials is, when we transform them, we can use the same transformations as we always have. We can move it up, down, left, right, flip it, shrink it, stretch it, do all of that. So here's what I'm going to do. I'm going to discuss all different transformations, we'll see a couple of them done live, and then we will take a look and see if we can recreate those transformations. Before we do, I want to remind you all something, that there are two types of transformations that we can do: vertical transformations and horizontal. When we think of a vertical transformation, we think of anything that changes the graph's height, or how high up or low down it is, or even just whether it's right side up or upside down. Vertical transformations are always going to apply to the entire equation. So for instance, if the transformation is plus 2, you're adding 2 to the entire equation. If you're multiplying by 2, you are multiplying everything by 2. With horizontal transformations, it's only going to apply to x, our input. So, as we go through and look at these, we should classify them as either a horizontal or a vertical. So, things like a horizontal translation will obviously be horizontal. Things like a reflection over the y-axis are going to be horizontal as well. Horizontal stretches and shrinks, you got it, still horizontal. So these transformations are only going to affect our x values. Anything vertical, however, like a vertical translation, a reflection over the x-axis, or a vertical stretch or shrink, will be applying to the entire equation. So let's take a look at some examples. Horizontal translations are when we want to move our graph left or right. And to do that, all we have to do is add or subtract from the x value. Again, it's horizontal, so we only apply it to the x. Let's take the examples that we have here. We have 4 to the x power plus 3, minus 3, and 4 to the x power plus 2. If we take a look at this, minus 3 means that we move it 3 units to the right, whereas plus 2 means that we move it 2 units to the left. It's sort of the opposite of what we think. So let's see them all in a graphing calculator. Our original is going to be 4x in the blue. There we go. We then shift this one to the right 3, and we shift this one to the left 2. It's all the same curve, all the same sort of rate of change, just in different positions. Again, this is 4 to the x power, 4 to the x minus 3, and 4 to the x plus 2. On the other hand, if we wanted to move it up and down, we could do a vertical translation. It's the same thing, just adding and subtracting, except if we want to go up, we are going to add to the end. So to move 5 units up, we add 5 to the very end. If we wanted to move down, we would subtract from the end. So all translations are just adding and subtracting. If we take a look, there's our original. The red one is 5 units up, and the black one is 1 unit down, because these are the equations that we put in, same ones that are in our notes. Then we have reflections. Reflections you can think of as flips. Now, I want to remind you all that with these flips, if you are flipping over the x-axis, it means you are flipping a point from up here above to down here below, or vice versa. That is a vertical change, so x-axis flips will be applied to the entire equation. If you're flipping it over the y-axis, it means you're flipping it left and right. Since that's a horizontal change, it's only going to impact our x values. So when we see something like 4 to the negative x, all we did was we took 4 to the x and put the negative on that x. It's a horizontal change. In fact, if we compare these two, let's take a look at the original and that 4 to the negative x power. There's the original. 4 to the negative x power looks the same, but it starts on the left and gets closer to 0 on the right. On the other hand, if we wanted to flip the entire thing, you see how we put this negative in front of everything? That implies that that is going to be a total change. It is going to be a vertical flip. When we graph this, we see that we get the same start, but it goes upside down. Now, I want to remind you of something very, very important. When it comes to reflecting, let's say we were reflecting f of x equals, I don't know, we'll stick to the 4 to the x example. Let's say we're reflecting 4 to the x plus 2, and we wanted to flip it over the x-axis. Well, since it's flipping over the x-axis, that's a vertical change, so we know this is going to be vertical. We know we're going to apply the negative to everything. Be very careful, because when you have different terms, you want to still make sure that that negative applies to both of them. The way to do this is to put your function in parentheses and put the negative in front of the parentheses. This is what it would be to flip this upside down. Finally, we have horizontal stretches, shrinks, vertical stretches, and shrinks. Remember, when we're talking about vertical stretches and shrinks, the number you see is the number you get. So if we wanted to stretch 4x, or 4 to the x, by a factor of 3, we are going to be multiplying it by 3. We are multiplying the entire thing by 3. This is 3 times 4 to the x power. I put it in parentheses just to be safe. So 3 times 4 to the x is going to look like this. You can see it? There's our vertical stretch. That is a vertical stretch by a factor of 3. It's growing 3 times more. Here on the blue, we have the 0.01. Here on the red, we have the 0.03. And if we look on the table, every red value is 3 times bigger than the blue value. That's what it means to be a vertical stretch. On the other hand, if we wanted to do a vertical shrink, all we would need to do is put a fraction in front instead. So what I'm going to do here is I'm going to insert a fraction 1 over 4, just like this example. This will be a vertical shrink by a factor of 1/4. It'll become 1/4 the height. Let's take a look. And there it is. It doesn't look like 1/4 to us, but if we look at the table, we see that every single blue value is divided by 4 when we look at the red values. 4 is 1, 16 is 4, 64 is 16, and so on and so forth. Things change when we go into the horizontals. So, when we see a horizontal stretch or a horizontal shrink, we actually flip whatever number they give us. So if they give us 1/2, and we're trying to do a horizontal shrink, that's actually going to be the same as multiplying by 2 on our x. It's the opposite. Another way to think about it, which I've said before, is a horizontal shrink is a lot like a vertical stretch. They're not the exact same, but they're similar enough where you can compare the two. So, if we wanted to shrink by a factor of 2, that means, by a factor of 1/2, it means that we're multiplying our x by the opposite of 1/2, 2. If we graph it, this should be a horizontal shrink. It should be scrunched up horizontally, and it is. So that's for a horizontal shrink. For a horizontal stretch is analogous to or similar to a vertical shrink. So we're actually going to replace the two with a, let's say, 1/2. This would be a horizontal stretch by a factor of 2, because the opposite. If we graph it, we should see that we get a little bit wider horizontally, and there we go, it's a little bit wider horizontally. So let's take a look at some of these functions down here. We're going to translate some exponential functions, and we're going to also translate some natural base exponential functions. What I'd like you to do is I'd like you to look at these 4 problems and try to identify what the transformations are on your own. In about a minute, I'll show you what the answers all are. So pause the video and try it out. All right, y'all. So for the first one, since we have a -4 at the end of our equation, or applying to the whole thing, we know it's vertical. Since it's minus, we know it's going to be a translation down. And since it's -4, it's a vertical translation down 4. Down below, we have horizontal transformations because they're only happening to the x. The 3 on the bottom here hasn't been touched in any way. So the fact that we have a -5 at the end tells us this is going to be a horizontal translation. And remember, when it's a minus next to the x, it's going to actually be to the right. So this is to the right, 5. The 3 that's multiplying the x, once again tells us that it'll be horizontal, but be careful. Horizontal stretches and shrinks use the opposite numbers from what they're supposed to be. So this 3, because it's horizontal, we know should actually be a factor of 1/3. This is going to be a horizontal shrink by a factor of 1/3 because it's the opposite. Over here with the +2, we know that's going to be a vertical translation up 2, because we're adding 2 to the end. And since we're adding 2 to the 3, we know it's going to be a horizontal translation left 3. Finally, and this was a tough one, you can even see that I accidentally wrote something and had to cross it off. We're starting with e to the negative x, so that negative sign is supposed to be there. But what is different is this -1/8. There are actually 2 transformations happening here. The first is a vertical shrink by a factor of 1/8. Because with verticals, it's exactly as it says it is. 1/8 means we're shrinking by 1/8. The negative sign that's applying here is a different transformation. Anytime we see a negative, it's a reflection over, and since here it's applying to the entire equation, it's going to be our x-axis. Very nice. Let's flip over to the other side and see what we can do with logarithmic functions. Now, logarithms are the inverse of exponentials. So if I really wanted to, I could plot an exponential and its logarithm pretty similarly. Let me show you. If I wanted to do, let's say, 10 to the x power, sorry y'all, if I want to do 10 to the x power, its inverse would be just log base 10 of x. And log base 10 we can always just write as log, so it would just be log x. If I graph this to compare, we see that the two of them are perfect inverses. They are flipped versions of each other. When we have a graph of a logarithmic function, then, instead of it facing like this, it's actually going to be the opposite. It's going to be like the other part of a hyperbola. It's actually going to be like so. The parent function, f of x, can be written one of two ways. Either you are using a common log, or any other log. You could put a base there. You could say log base b of x. Or you could also do this same graph with a natural log, ln. And the base for ln is secretly e, the natural base. But the transformations are all the same. We just have to be careful. We have to be careful because here, x is at the very end of our equation, instead of sort of on its own space. What that means is, if you want to add or subtract something specifically from x, you do need to put parentheses around it. For instance, if I wanted to move right 5, that'd be the same as subtracting 5, right? Well, if I have log base b of x and put a minus 5 at the end, that's moving it down 5. We need these parentheses to show that it is now a horizontal change, that we're only putting minus 5 on the x, not on the entire thing. Still, the transformations are all the exact same, so horizontal translations are going to involve adding or subtracting from x, whereas the vertical ones are adding or subtracting from the end. You can see these in the examples. A reflection over the x-axis is going to be vertical, but a reflection over the y-axis is horizontal. So the first one is a reflection over the y-axis, because it's only affecting the x. When the negative's in front of the whole logarithm, it's a vertical, because it's changing everything. For a horizontal stretch and shrink, remember that the numbers are the opposite of what you think they are, and they're being multiplied to the x. For a vertical stretch and shrink, remember that you're multiplying the entire logarithm by some number. I do want to mention, our notes have some kind of funny errors. For question A, it says log. We don't need 2 logarithms. That was just a doubling up. On the other hand, B doesn't have a log at all. So for B, we can rewrite this one as log base 1/2 of x, because that's how it was supposed to be before the error. Going from log x to log of negative 1/2 of x, we have to think about what's changing. Since it's only our x being changed, these are both horizontal transformations. Multiplying x by 1/2, well, remember, when you have a horizontal stretch or shrink, it's the opposite. So this is really like multiplying it by 2. This is a horizontal stretch by a factor of 2. And that negative next to the x means it's a reflection, and the horizontal reflection is over the y-axis. Over on this one, we've got quite a few transformations. Well, specifically, there's 2 of them. This 2 is multiplying the entire thing, so that's definitely going to be vertical. But notice that the plus 4 is in parentheses with the x, so it's horizontal. We've got a horizontal translation here, and since it's plus 4, that's the same as moving it left 4. And since we're multiplying the entire thing by 2, that's a vertical stretch by a factor of 2. All right. Last, but most certainly not least, we have writing transformations. These ones aren't as tough as you think. It's just a matter of starting with f of x and working our way over to g of x. So starting at f of x equals 2 to the x power, we need to do a reflection in the x-axis, that's a vertical reflection, followed by a translation 4 units right, that's a horizontal translation, of this. So if f of x equals 2 to the x, let's not jump all the way to g of x right away. Let's do it step by step. I'm going to make a new function called, I don't know, we'll call it h of x. You could call it whatever you want, though. H of x is the transformation I want to do with just reflecting in the x-axis. Since it's a vertical reflection, the negative gets applied to everything. So it's negative 2 to the x power. Now we can go over to g of x, which is also a translation 4 units right of this. So how do we move something 4 units to the right? Well, recall that horizontal translations only happen to the x, so we're going to be adding or subtracting from the x. In this case, moving it to the right is subtracting 4. This is your final answer for g of x. G of x equals negative 2 to the x minus 4. Shall we check it? Let's take a look in our graphing calculator and see if this matches up. So if I'm graphing 2 to the x power, and I'm also graphing the translation negative 2 to the x minus 4 power, let's see how they change. The blue is our original. The red should be flipped and shifted. And it is. It's shifted to the right 4 and it's flipped upside down. Perfect! Let's see b then. For b, f of x is a logarithmic function, log base 1/3 of x, and we're trying to do, once again, two transformations. We want to translate 2 units up, and then do a vertical stretch by a factor of 2. Whoops. Should really put this in red because it's a vertical again. It's 2 vertical transformations. So first, to vertically translate 2 units up, all we need to do is add 2 to it, right? We add 2 to the end of our function. To change h of x into g of x, we not only add 2, but we also want to vertical stretch by a factor of 2. Vertical stretching means that we're going to multiply the entire thing by 2. So if we have our log base 1/3 of x plus 2, let me ask you, would this be the correct answer? This would not quite be the correct answer. Remember, we're not just multiplying logarithm of x by 2. That's what would happen if we put a 2 in front. We're also multiplying the plus 2 by 2. In fact, maybe to make this a little more clear, this plus 2 is being added to the entire thing. Just want to make it a little bigger so we can see that it's really adding 2 to the end. To make sure that we're stretching everything by 2, we put it in parentheses. With that said, that is the end of our notes for today. So thank you so much, everybody. I hope you have a fantastic rest of your day.